Welcome to This Explainer. Today, we're taking those invisible, microscopic forces that hold our entire physical world together, and we're turning them into a story. A story about atoms on this, well, epic quest for stability. I'm your host, and we're peeling back the curtain on the secret social lives of atoms. Think about it. The refreshing water you drink, the complex double helix of your DNA, even the rigid steel beams holding up skyscrapers. Literally every aspect of our physical reality comes down to atomic relationships. So, we're going to explore exactly why and how these tiny building blocks decide to team up, share resources, or, in some cases, outright steal from one another to build the universe as we know it. Okay, let's dive right into a really fundamental question. If atoms are all around us, why do they almost never just chill out on their own in nature? I mean, unless you're looking at that rare, very specific group called the noble gases, atoms just do not like being alone. They are inherently restless. They're constantly seeking out partners to form molecules and complex compounds. But what's actually driving this relentless microscopic matchmaking? What unseen force compels, say, a sodium atom and a chlorine atom to find each other and fuse together? To make sense of all this, here's our game plan for today. We're going to start with the quest for stability, define the golden octet rule, compare covalent and ionic bonds, meet the notorious rule breakers, and finally, look at measuring the bond. Let's get into it. Section 1, the quest for stability. This is really all about nature's way of lowering energy. So the absolutely crucial thing to understand here is that isolated, independent atoms are just bursting with high energy. And if there's one thing the universe despises, it's high, unstable energy states. It's a fundamental rule of thermodynamics. So, joining forces through chemical bonds is basically an atom's ultimate solution to finally relax, lower its energy, and become chemically stable. It's kind of like a heavy boulder perched precariously at the top of a steep hill. Naturally, it wants to roll down to the valley floor to lower its potential energy, right? Well, an atom desperately wants to lower its chemical energy in the exact same way. Bonding is nature's elegant, microscopic way of finding that peaceful valley of stability. When they bind together, they release energy into their surroundings, actively creating a much more stable, grounded system. Moving on to Section 2, the golden octet rule. It all comes down to the magic number 8. Okay, now that we know atoms crave stability, what does atomic perfection actually look like? Well, back in 1916, scientists Walter Kössel and Gilbert-Lewis figured out that atoms use their outermost electrons, the valence electrons, as a sort of currency. They realized the inner shell electrons are safely tucked away in the atomic vault. They're protected by the nucleus, so they never really get involved in reactions. But those outer valence electrons, they are out there on the wild frontier, actively negotiating, trading, or sharing with other atoms to reach a highly coveted, mathematically stable configuration.
And that brings us to the magic number 8. Having 8 valence electrons perfectly mimics the stable, naturally inert noble gases. You see, noble gases already have this perfect octet in their outer shell. Because their electron shells are completely full, they are existing in a state of ultimate thermodynamic peace. They don't need to react with anybody. So pretty much every other atom on the periodic table is essentially playing this frantic game of catch-up. They're continuously rearranging their electron configurations, desperately trying to scrape together exactly 8 valence electrons so they can finally hit that low energy bliss and just chill out, exactly like a noble gas.
Up next, Section 3, covalent and ionic bonds, or as I like to call it, the art of sharing versus transferring. Atoms basically have two options to reach that magical 8, and the path they take depends entirely on how hungry they are for electrons. Scientists call this electronegativity. If two atoms have a similar hunger, they cooperatively share electron pairs in what we call a covalent bond. Think of it like two neighbors pooling their money to buy a lawnmower that they both use. But if one atom is a massive bully with a much stronger pull, we get an ionic bond. This isn't sharing, it's a complete transfer. One atom violently rips an electron right away from the other. The thief becomes a negatively charged anion, and the victim becomes a positively charged cation. And then boom, they are locked together by the powerful electrostatic attraction of those opposite charges. Now take a look at this. The table salt you sprinkle on your food, sodium chloride, arranges itself in this perfectly orderly three-dimensional lattice to absolutely maximize its stability. When sodium and chlorine form those ionic bonds we just talked about, they don't just pair up into cute little isolated couples and float away. No way. Because they're positively and negatively charged ions, they pull on every single oppositely charged ion around them from all directions. This creates an incredibly dense, repeating geometric crystal. It's this massive 3D grid that perfectly cancels out the charges. And the sheer amount of energy released when this tight lattice clicks into place, that's known as lattice enthalpy, is exactly what makes solid salt so remarkably stable. So, what happens when atoms share electrons in covalent bonds instead of forming those rigid ionic crystals? Well, we use a clever little bookkeeping tool called formal charge to track the electron currency and find the most stable structure. Since the electrons are being shared, we essentially have to act like microscopic accountants to make sure no atom is carrying too much of the burden. We do this in 3 logical steps. First, we count the total valence electrons the atom originally brought to the table. Second, we subtract the non-bonding electrons, the ones the atom is keeping entirely to itself. And third, we subtract exactly half of the shared bonding electrons. By running this quick audit, we can evaluate different possible structures for a molecule and confidently say, yep, the one with the smallest formal charges is our lowest energy winner.
Which brings us to Section 4, the rule breakers. This is what happens when atoms rebel against the octets. This is where things get really interesting, because in chemistry, just like in life, rules are occasionally meant to be broken. These are the atomic rebels that absolutely refuse to conform to that golden number 8. First up, we've got the incomplete octets. Smaller elements like lithium and boron start with so few valence electrons that they're actually perfectly happy settling for a stable configuration of just 4 or 6. Next, we have odd electron molecules like nitric oxide. Because they literally possess an odd total number of electrons, mathematically, someone is always going to be left without a pair, yet somehow they remain stable. And finally, the expanded octets. Third-period elements like phosphorus and sulfur actually have access to empty 3D orbitals. They treat these extra orbitals like an empty attic space, packing in 10 or even 12 electrons, completely blowing right past that 8-electron limit. But wait, it gets crazier. The entire foundation of the octet rule is based on the rigid assumption that noble gases never ever react. Yet, scientists made a truly shocking discovery. Even noble gases like xenon and krypton can actually be forced to form chemical bonds. Back in 1962, a chemist named Neil Bartlett completely shattered the original Kössel-Lewis paradigm. He figured out that if you trap a larger, heavier noble gas in a room with extremely reactive, highly electronegative elements, like fluorine or oxygen, the intense pull of those elements is actually strong enough to rip electrons away. So yeah, even the absolute laziest noble gases will get pulled into a chemical relationship, proving the true inertness is sometimes just an illusion. All right, moving to our final segment, Section 5, Measuring the Bond. Let's look at the parameters of atomic relationships. So having met both the rule followers and the rebels, how do we actually measure the strength and size of these invisible connections? Well, just take a look at the relationship in this table. The higher the bond order, meaning whether atoms share 2 pairs in a double bond or 3 pairs in a triple bond, the closer the atoms are violently pulled together. Look at carbon. When carbon atoms share just a single pair of electrons, they sit at a pretty comfortable distance of 154 picometers. But if you force them to share 3 pairs in a triple bond, the immense electrostatic attraction between those positively charged nuclei and that massive cluster of shared negative electrons completely overpowers their natural repulsion. They get squeezed tightly together to a remarkably short bond length of just 120 picometers. And this brilliantly illustrates the golden rule of bond parameters. As the bond order increases and those atoms are pulled closer together, the bond enthalpy, which is the sheer amount of energy required to rip them apart, absolutely skyrockets. I mean, a single bond takes a modest amount of energy to break, but snapping a triple bond, that takes a massive Herculean amount of energy. To put that into perspective, consider nitrogen gas, which makes up about 78% of the air we're breathing right now. It's held together by a tight triple bond, making it incredibly tough to break apart. That immense bond enthalpy is exactly why nitrogen is so famously unreactive and stable in our atmosphere. It simply takes way too much energy to split those atoms up so they can react with anything else. Finally, scientists measure the sheer physical size of these microscopic structures using advanced X-ray diffraction, capturing 2 entirely different dimensions, the bonded covalent radius and the overall van der Waals radius. Notice how, when atoms form a covalent bond, their dense electron clouds actually physically overlap and blend together. The distance from the center to that point of overlap, that's the covalent radius.
But the van der Waals radius is completely different. It basically represents the entire personal protective bubble of the atom, including all the vast, non-bonded regions of its valence shell that are pushing against neighboring molecules. It is the ultimate measure of an atom's true microscopic footprint in physical space. So what does this all mean? Well, since our most foundational rules of chemistry are built on assumptions that even nature itself sometimes breaks, what other invisible forces and rebellious elements are just waiting to be discovered by curious minds like yours? We started this explainer looking for perfect atomic stability and the holy grail of the magic number 8. But as we dug deeper, we uncovered a universe practically overflowing with bizarre exceptions, wildly expanded octets, and surprisingly reactive noble gases that just refuse to play by the rules. Keep questioning the established models, keep seeking out the bizarre exceptions, and most importantly, never stop wondering about the incredible, invisible social lives of the atoms that hold our entire universe together.